Hello, my name is Pablo Rivas. Today I'm presenting on behalf of our interdisciplinary team with respect to a work entitled Bottleneck-based Encoder-decoder architecture for learning unbiased consumer-to-consumer image representations. I would like to start by introducing the big picture of the problem we're trying to solve. We have source of information as posts on consumer-to-consumer marketplaces. These have title, images, and body of text. We would like to train this as a shared feature encoder that will take text and images and learn from the text and the images in separate ways, but in ways that are being known to be successful, for example, using BERT or masked learning, or the type of sentence embedding for text, and also similarly for images. And in the end, fine-tune these models into into a way that will allow us to predict the probability or the risk of a post containing some type of illegal activity. We specifically focus on human trafficking and the trafficking of stolen goods. The problem we're trying to solve really involves an image encoder and a text encoder in a general sense. So we're trying to initialize this process with no supervision or self-supervised approaches to learn these encoders, either doing contrastive or a reconstruction or variational type of losses or approaches. And then go through a few shot, weak supervision, fine-tuning, so that we can perform classification or regression in the sense of detecting trafficking or illegal trafficking in these online marketplaces. To understand better the constraints we have, just imagine the cost of download is $131,000, and it's very prohibitive to actually use DALL-E or train from scratch or fine-tune it ourselves, or even GPT for that matter. These are extremely costly, though very successful architectures. We will focus on lightweight encoders, specifically images in this particular research. To understand better the challenges with data, just here's an example. A post can have a title of the post can have text, number, and emojis. But within the title, there are typos, there's slang, and there's codes that people use, especially in organized crime, that could contain important information that we cannot just get rid of. So we need to take into account models that don't just eliminate slang or codes or typos from text, but actually look into what that means in a bigger context. There's also pictures in the posts that can contain actually no pictures or many. Most of these are in controlled scenarios and may contain people in them. So we need to protect the privacy of these people. Also, if there are any phone numbers in there, we need to hide those plainly available identifiers. And not only that, in the case of human trafficking, these pictures could be graphic, and we need to protect our researchers' mental health, our students and faculty, that and prevent them from being exposed to that. So we want to find embeddings of pictures to work with rather than looking at the pictures themselves. Finally, the body of the text contains the same challenges of titles, but also there's usually some type of deception involved or very incomplete sentences, and they can have variable length. For example, a post can only contain a phone number, and that's all it has. Or it can have also many paragraphs of information describing a service or a part of a vehicle. So these are the challenges we have with the data. Although we focus on images, research later will be combining text as well. So focusing on images, we know about the very successful vision transformer that looks into patches, pays attention, on specific parts. We can do training by looking at this encoder-decoder architecture of vision transformers. But it was originally intended for classification, and it learns really good representations, although it's oriented to classification. But on top of that, it's extremely costly to train this. It's a huge model. In the base model, the smallest one of 86 million parameters, and there's a larger model that is over 500 million parameters. So these are extremely costly items to train. So the other approach would be to use a bring your own latent. And although this is a very interesting approach that gives you the freedom of bringing your own embedding method or architecture, like a ResNet or an efficient net of some kind. The idea is that you do bootstrapping and from the source, and you're trying to align those projections. And at the end, the features that it learns, the embeddings are really rich. But again, this is very, very large info model. So training it is extremely costly for us. So we're looking for something lightweight. Mentioning clip here as something that looks similar to what we're envisioning in the end, in the sense that we're going to have an image encoder and a text encoder, and align them using contrastive or other self-supervised type of learning. The idea here is that the contrastive training of this type of encoder, usually for it to be successful, as CLIP is, these models are huge and costly to train. And so we're looking to focus on this part, although in the big picture, our end goal would look like CLIP, but we're trying to make it as efficient as possible and in different way, but we'll focus on image encoding. So our proposed architecture is as follows. We're going to use convolutional LSTMs. Traditional LSTMs are extremely costly because they use dense network. But if we use convolutions in some parts of the LSTM, this will yield very good savings, and also will embed information across the temporal, in this case, channels of a color image. Let's talk about every part here that includes these residual connections. First, we go with the perceptual feature encoder. These are back-to-back convolutional STMs that are meant to embed information, encode it, and reduce dimensionality as you go through using strides to our advantage. And the idea here is that it uses no residuals yet, so it is pure feature encoder. The next piece, though, uses the perceptual features plus the residual from an original image that's been downsampled. So we're trying to entangle features here, perceptual features of the input. Then we go through a bottleneck that will yield our latent representation. And then from there, we decode using dense decoder and then traditional convolutional networks that do upsampling in a very similar way that super resolution does. And then we reconstruct back the input. This model is trained using augmentation that varies the angle of the image and varies the position or the focus of the image. Is used with traditional training using Atom and the traditional paradigms to stop and decay as well as you learn. Our results suggest that the model it is very scalable with respect to the number of images that you're training or your data set. And also, when you look at the clusters, these have higher quality. This clustering has been done with k-means in a high dimensional space, not in the two-dimensional space. We're showing it in 2 dimensions as an example. But the features and the learned are clustering things together according to perceptual features. Some of the things we find the centroids are by the objects they're in, the absence of objects, and also color-based features. We cannot show what the centroids are specifically because it's graphic content, but the model is able to perform really, really well. In conclusion, we learned that doing this lightweight model will yield very good representations with fewer parameters, and we were able to hide also personal identifiers, and not only that, but protect the mental health of our researchers by using the embeddings alone. If you have machine learning questions, please contact me or contact Dr. Stacy Peters for human trafficking related questions. Thank you for listening.